So, we'll dive in today. We'll do a couple. We'll spend some more time right now, right here in this same section. We want to get to the place where we can use this a little more fluidly. In particular, our goal today is to manipulate power series. So take known power series that we know and love, and then see if we can come up with power series expansions for other functions that might be really hard by using various combinations of functions, compositions, and sums and differences, and products. So we'll take a look at that in a minute. One other thought I had too as we're thinking about this Taylor expansion stuff, this idea of needing like an infinite number of derivatives is, I'll put these back up here too. So this is actually deeply philosophical. I want to make sure you understand what we're really saying here. Imagine that let's talk physics for a second, that you have a particle that right now you know its position, you know its velocity, you know its acceleration, you know its jerk, its snap, crackle, pop, you know all of its derivatives all the way out to infinity, say. If you happen to know right now all of those things about a particular particle that's in motion, then there's a sense in which, do you not know then where its complete trajectory will be out into infinity? I mean, this is a deeply philosophical thing to think about, because really that, in some sense, violates our notion. I mean, it's a very deterministic worldview you have to adopt to really go there, right? I mean, does that particle have, we're saying we know exactly what it's going to do forever. If we know everything about its current state, all of its current derivatives, all the way down, then we know exactly where it's going to go from here on out. That's what we're saying, right? We could come up with a series expansion that gives us the entire function going out. It's a pretty powerful idea. In fact, yeah, that kind of thing. I read an article about underwater, very, very deep down underwater where GPS doesn't work, submarine, autonomous submarine that does underwater exploration. Johns Hopkins put it out. And the way that it tracks where it is it says it kind of integrates along the way. It knows its own velocity and its acceleration, and so it can figure out along the way where it is. It can track its position by integrating what it's doing, right? It can be like, well, I've moved this far, I've been moving at this velocity, so I know where I was, and it can back integrate. So the point is, if you know all of the information about derivatives, then you know exactly where you're headed, what you're doing the whole time. Yeah.
That is a Pi 18 article yesterday. I saw like some mathematician made a proof of why e raised to the pi is equal to 0.
Yeah, and actually we might have a proof of that even, in the next 24 hours here with some of these series, right? The proof I go for, there are lots of actually nice proofs of that, but the proof I would go for is a series, use the series expansion for e to the x, sine x, and cosine x to prove that e to the I theta is equal to cosine theta plus I sine theta. Yeah. So we saw the Taylor series expansion for sine x yesterday. So we'll come up with a series expansion for the other two today, and you might be able to prove it before the sun goes down today using Taylor series. One thing that we did yesterday was find the series expansion for sine x, and we put it up on the board too, really nicely. It looked a little messy, but in the end, it was just like odd powers, all that kind of stuff. X to the 2n plus 1 over 2n plus 1 factorial times -1 to the n, all that. But that was centered at 0. So let's just practice. I think this came up in your homework a little bit, right? You're centering at different places. So let's just try, practice here, centering it somewhere else, just so you understand that as we come up with a power series, we have options. Is there only one series expansion for sine x? The answer is no. We came up with, I think, the most common one, the one we're going to probably most often go for yesterday. But let's try it centered somewhere else just to prove that you can do it. And I think this isn't too different from your homework, so I'll just invite you to try. Go ahead. We'll come back together in a second. Exactly. So if you haven't already done so, you're taking a bunch of derivatives of f of x. Geez, my board seems to be, oh, there we go. Now it's okay.
When we say how far to go, what should we do?
Well, ideally you would come up with a rule, right? If you can. But it's our fault for not being more specific, I guess. Already, those who are doing this are thinking, as you're starting to plug things in. Yesterday, you noticed if we were centering it to 0, it was very nice, wasn't it? Because if you center it at 0, all sorts of terms go away. We get only, if we're centering it at 0, we only get odd powers. Right? But that won't be true here. Do we get a bunch of 0 terms here? No, not this time, right? So as you plug in pi over 3, you get actual, like, real non-zero values along the way. Okay, now we need to remember our trig here. Sine of pi over 3. Cosine of pi over 3. But I do see kind of a little bit of a pattern. So maybe this isn't so bad. And can we assume that this pattern continues? Yeah, I think so. Yeah, so we're good. So if you plug in pi over 3, can you just confirm that you're getting what I'm getting? So and there are lots of different ways you could expand this. Here's another expansion for sin x. We just want to show that there are other ways to expand sin x, centered at pi over 3, say. Why would you want to center it at pi over 3, by the way? Why would you want to do that? One reason would be to make, maybe you're estimating values of sin x that are near pi over 3, so you want an expansion around pi over 3. So if you're trying to estimate the sine of 100, you might not want to use the series for sine centered at 0, because it converges slowly all the way out to there, right? So you might want to center your series at 100. So that would be a reason. Why would you want to use these series expansions at all to evaluate things for sin x is another good question. And the answer is, I guess actually that's flipping the question. Why would you? How does someone actually write a computer program on your calculator to evaluate the sine function? Have you ever stopped and actually asked yourself how the calculator, it's magic, right? You just like ask your calculator what the sine of an angle is, and I'll give you a hint. They use series expansion underneath on your calculator to get very precise, arbitrarily precise values of sine, right? So you're begging the question if you're asking, like, well, I don't need the Taylor series. I have the sine function on my calculator. That's what it's using, right? I just want to make sure we're clear. We're not putting the cart before the horse here. That's exactly what's happening here. All right, so if we learned something from yesterday, what's the first term? Root 3 over 2. Yeah, just this guy. Plus 1/2 times x minus pi over 3 plus, or minus, I guess we could say. I'm going to fix that 3 there too on it. Minus root 3 over 2 over 2. So if everyone's okay with that, we'll just write it. Root 3 over 4, we'll say. Minus 1/2. Oh wait, not 1/2, but yeah, 1/2 over 3 factorial, or 1/12, times x minus pi over 3 to the 3rd. Okay, etc. Maybe that's enough to kind of write down. But actually ask a good question. What's being expected of us as we actually give the answer to this question? Because it seems like maybe we're done. I think that if you were really to write a rule for this, I'm trying to think if you could write a rule for this that was nice. The way I might have to do this one is to write a rule that was piecewise and say, for all the odd indexed terms, here's the rule. For all the even indexed terms, here's the rule. Does that make sense? I think we won't do that right now, but I think you could if you really were to press us. Because don't all the even terms have a very similar form, and all the odd terms have a very similar form? You can see that already over here, right? So I might write it that way, maybe. but I think we can maybe leave it right there for now, even though it's maybe a little bit tricky to write the rule. In fact, for many series that we're going to encounter, it will be difficult or impossible to write a rule for it. So someone will just say, okay, you don't need to write the rule, but at least please come up with the first 4 terms to show that you can. And then we'll assume that if we needed to, you could find a 5th term too, just to prove that you know how to do it. Well, this is a powerful moment. Let's expand e to the x around 0. And of course, this is our joy, isn't it? F of x, f prime of x, f double prime, f n of x, the nth derivative of e to the x. All of those are this we couldn't possibly be asking. You thought that that sine x was fun to expand. Well, all of these are e to the x. So that means that, of course, f of 0 and f prime of 0, all of these are what? E to the 0, right? Which is what? 1. Okay. So now I think we're ready to do our Taylor expansion right now. Right now we're ready to write it down. So here we go. F of x, or I guess we could write e to the x. This could be possibly an easier one to do, right? What's the? I should call. Let's have. I feel like at this point we should know what we're doing. So I'm gonna start calling people. You left. Alexis, you want to give it to us? Walk us through here. Yeah, I'll give you a chance to think about it for a second. Everyone, write down what they think the Taylor expansion is. We've kind of done the hard work here for you a little bit. Okay, go back to the rule. Remember, it's for each power. It's centered at 0, so all of our variable parts will be x to the power, x to the power, x to the power. What are the coefficients? Remember what we said. We cannot underestimate the importance of this. The nth derivative of the function evaluated at the center divided by n factorial. Cannot say that enough. Here it's not too bad. I'm buying you some time, Alexis, whenever you're ready. What do you think? Comes out really beautifully, doesn't it?
Yeah.
What do you think? What's the first term? Yeah, so the first term will be just a constant. What's the constant, the very first term? It's what? Yeah, it's 1, right? Because that's f of 0. Keep going. Plus. Yeah, so then the second term, let's help her out here. So what? It's something times x to the first, right? So what is that something? What's the coefficient? That first coefficient for any Taylor series is the first derivative divided by 1 factorial, right? So what is that? Well, keep in mind, it's always the, let's write this up here just again. Cn, we'll call that the coefficient on the nth degree term, is always f, the nth derivative of f, evaluated at whatever the center is. For us, that's 0 right now, all over n factorial. That's the coefficient on x to the n, or x minus a to the n, rather. So so this one here is going to be x, right? But what's the coefficient on it here? Don't think too hard. If this is the first degree term, we have n equals 1 here. So what's the first derivative? At 0, like everywhere, it's 1. And what's 1 factorial? So in fact, maybe we just leave it like it is, right? So now what do we need on x squared? It goes out front there. Yeah. Yeah, it's 1/2. Why? Exactly. And what are all the numerators on these? 1, right? We just established that all of these are going to be 1 for us right now. What's the next one? Keep going. Etc. Do you want to give me an actual series for this? N goes from 0 to infinity. What's the rule? What do we have? It's always what's the rule in general? It's x to the n over n factorial. So we've come up with a series expansion for e to the x. By the way, this particular thing is not written on the hallway out there, but in the hallway we have e equals 1 plus 1 plus 1/2 plus 1 over 3 factorial plus 1 over 4 factorial, etc. That gives you an expansion for e if you like. Feel free to, you can already, do you see that that equals e? 1 plus 1 is 2.5. Already we're getting close to e. This picks up some more loose change as well. So this does converge to 2.71828. If you plug in, what did I do to get this series? I just plugged in, of course, 1. Yeah? So that's one thing that is painted on the hallway down the hall. And then centered at 1. I don't think I have more room on the slide here. Let's do that here. Try and fit it down here. At 1, obviously we still have all the same derivatives, but f of 1 is equal to, now we're plugging 1 into these different things. So we get e to the 1, and that's for all of them, right? Again, we get all of these derivatives will be e, and so this doesn't change that much. So give us the expansion for this. And Ani, can you take it? What do you think? So another series expansion here would be e to the x could also be, what's the first term here? But we're using these now. Okay. Plus. Well, this is term 1 now. Yeah. Huh? Times ex. Well, now careful. Where are we centering it, though? Yeah, good. All right, keep going. Now you're in the rhythm. All right, that's enough. Right? Right? So she centered it there at 1 now, right? We haven't done cosine yet, so it's worth doing that. Let's do cosine. Take a second to do it. We haven't done it yet. It's not a huge shocker after having done sine yesterday. I think you're already even expecting there to be some kind of similar thing that happens given the way you know these derivatives go. Yeah. You can center it wherever you like. I think that we would all probably prefer to do 0, though, don't you agree? If I gave you free choice, you would still pick 0. So yeah, let's pick 0. So at 0, cosine is 1, so we start off with there. And then what's negative sine x at 0? 0. Okay, so we're just off the right start here. Just keep filling that in. Get some derivatives. Plug in 0 to all of them. You get this nice pattern, just like we got yesterday, right? We got a bunch of 0s and 1s and negative 1s. So all sorts of, we'll write it out very carefully, but already you know that a whole bunch of these terms are going to drop away. In particular, which ones will drop away this time? Yeah, notice that all of the the first derivative term that goes with the first order term, the third order term will drop away. We can already see that's what's going to happen. So we're only going to have remaining just even powers of x, aren't we? We can already see that happening maybe. So here we go. 1 is the first term. Plus, we'll write this with zeros, but then we'll let them drop away in a minute. 0 over 1 factorial times x minus 1 over 2 factorial times x squared plus 0 over 3 factorial x cubed plus 1 over 4 factorial x to the 5th, etc. So what are we getting here if we clean this up without all the zeros in there? We get 1 minus x squared over 2 factorial. Yeah, 4, sorry. Plus x to the 4th over 4 factorial. And if you agree, you can keep going a little bit further if you aren't seeing the pattern yet. But I think what we said was going to happen happened, right? We get all the even powers, and just like sine had alternating signs in front of all the terms, we have that happening here too. So one thing I want to make sure we kind of back away and look at too is we have a series for sine that looked like this. We have a series for cosine that looked like this, now with the even powers. E to the x actually looked somewhat familiar too, similar to these, didn't it? It was all these same things as well, with all the powers and no alternating signs, just to go back and see that again here, right? This is x to the n over n factorial, just in general. So now I'll ask you, Gabe, to go prove that now, right? Now you have a power series for e to the x, sine x and cosine x. See if you can't just plug in I x and prove Euler's equation. Give it a try. Plug in I x to these series and see what you get into e to the x. All right, so now we have a bunch of series now to work with, don't we? We have geometric series in general that are easy to use. We have sine x, we have cosine x, we have e to the x, and we'll come up with some other ones too, some other common ones as well. But I'd just like to show you how this would be difficult, this one here, if we were to do it from scratch, right? It wouldn't be that hard. Like if we just get like a 2 popping out every time, right? And it would work out really great. But what we can do is if we have a series for cosine already, and we do, let's just keep in mind that cosine u is equal to, because we just said so, 1 minus u squared over 2 factorial plus u to the 4th over 4 factorial. That's a factorial. Minus u to the 6th over 6 factorial, etc. You see where I'm going with this? What am I going to do? Instead of reinventing the wheel, what am I going to do here? Yeah, I'm just going to take that and let u be 2x. So here we go. Now we have to be a little cautious. I'll write this down, but then I'll give us a little caution here too. So you want to use, the point is right now, what kind of function combination are we dealing with here? Is this the sum of 2 functions? Is this the product of 2 functions? What are we dealing with here? It's neither of those things. It's what? Yeah, this is a composition of functions. So this is a good candidate for this, what we just did. So certainly if you have a composition of functions, one of which you know the power series of, you might be able to take advantage of that. We always want to though prove to ourselves that what we have here really is a power series. Because it would be very tempting to have, say you had the cosine of, I don't know, 2x plus 1 or something like that. Now we could rescue that. But if you have 2x plus 1 in here, then you don't really have yet really powers of x. We always want to prove in the end that what we have is some number times x to a positive integer power, plus some number times x to a positive integer power. And I think that's pretty clear here, but let's make it really clear. So what do we have here? We have, we could just write 2 squared. I don't know if we want to write, so we have 2 squared over 2 factorial, x squared plus 2 to the 4th over 4 factorial, x to the 4th minus, I just want to isolate that coefficient to prove to all of us that what we have here really is, all the way along, some number times x to the, a positive integer power, right? So I think I just want to make sure we're clear on that. And just let's also write the general term here maybe too. This is good practice. You got an x to the, how would you like to do this? If we start, we can index this however you like. Maybe you want to start with an index of 0 here, or would you? Yeah. Okay. It seems like you guys like 0, but it doesn't matter. So if you want to start with 0 here, what do we have? This is x to the n then. What's the coefficient? You want to help me out with that? Certainly n factorial downstairs. No, it isn't. Well, actually, wait, hold up. It's not n. We don't want to just say n. Maybe we want to say, what'd you say? 2n, yeah. And down here, maybe 2n factorial. Okay, so I think we're making progress. What else do we need then? Up top, we've got 2 to the 2n. And then the only other thing we're missing is what? Yeah, we could do -1 to the n out front maybe. And I think I'm running out of space here. Is that good enough? Some triple dots in there. Yeah, so it's good practice. So sometimes these instructions will say, if it's actually able to be done, they'll say on a problem, write the first 4 terms, or the first 4 non-zero terms or something. Other times it will say, write the first 4 non-zero terms and the general term. And by that they mean, write this please, right? Write the first 4 non-zero terms and the general term. They'll give those instructions. Or sometimes we could ask you to write a summation notation. But we'll only ask you to do any of those things when they're possible. Yeah. Yeah, like I said, you have to be a little cautious that what you get is actually a power series in x, right? Like it would be, like say you had cosine of I don't know, cosine of e to the x or something like that. It would be very tempting to be like, oh, all I have to do is use the power series for cosine, plug in e to the x. Oh wait. I mean, you'll get something that's perhaps true in some, but it's a little prickly. It is in fact not a power series if you have powers of e to the x in here, right? You have to be able to write it as this, something times x to a power. But be careful, because once we introduce some of these crazy ways to manipulate series, people can sometimes go off the deep end, right? You want to make sure you can always come back to this kind of form. All right, what are we going to do here? What kind of combination of functions do we have here? Anyone have a strategy for picking this one up? Let's just acknowledge that if we tried to find the Taylor expansion by hand of this, it wouldn't be super fun because we have product rules to do. And every time you do a product rule, you have more product rules to do as you took a second and a third and a fourth derivative. And suddenly the derivative would be like many terms long. So it wouldn't be real fun to do this one by hand, but we can easily get this one by doing what? When we hack our cosine series, what do we have to do to our cosine series? Let's actually use like the law of replacement. What is cosine x? Again, we need to understand that these are interchangeable. By cosine x, we also mean, friends, 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th. Isn't that what we literally mean by cosine? We maybe are still uncomfortable with that, but that's exactly what we mean. Right? Well, I think that suggests already what we're going to do. Right? What are we going to do? You see the power series of the thing we want? Just multiply everything by x. And if you want to adjust the rule for cosine, just up the power by 1. Right? That's what you've just done. You just added 1 to the power on all these. And it's pretty clear here that what we get is is still a power series, right? So we're okay doing that, I think. So we still have 6 factorial on the bottom there, but a 7, x to the 7th on top. And that's definitely a power series expansion for this function. Anyone, any other thoughts there? We could practice writing the rule too. That'd be good to practice that. Stop us if you have a question. We're in deep here. So I want to make sure if we need to climb the ladder of abstraction and climb back down, we could do that. Stop and be like, wait, what are we doing again? Feel free to ask anytime. I think we do need to, even if we fully understand what's going on, we need to stop every once in a while and just appreciate the fact that what we're doing here is taking some crazy function, x cosine x, this crazy periodic function, and we're writing it as a polynomial. We can't lose sight of that. This is really a powerful thing we're doing. It's worth mentioning now, kind of taking inventory of where we're at. So these all appear in a nice plate in your book. I have all these series listed, but I'm just going to remind us of where we're at. Use geometric series whenever possible, right? Because there's really not very much calculus needed there. You just use your series expansion result from pre-calc, right, to get the series. And you've seen how you might think, oh, that's a limited case. No, it isn't. We've seen how expansive it is over the last couple of days. We can try and manipulate things to get them into this form, and then, you can just use the to do that anytime when possible. Here's the ones we've just recently derived. E to the x just today. Now I'm giving you, over here, we all know, and we've proved before in your life that this is true, right, that it converges here. I'm giving you right now, but it's not hard to prove, we'll prove maybe in the next couple days here, that this actually, the e to the x series converges on the whole real line, right? It's pretty to watch. Sin x we got yesterday, there it is again. It's all the odd powers over that odd number factorial and alternating signs. Converges on all reals. Cosine we just derived today, also converges on all reals. Same thing as sine, just with all the even powers instead, right? And these, and a few more, a series for the natural log of 1 plus x, a series for tangent, I think, appears on page 491 of our book. So these, along with some other ones, appear on page 491 of your book. So when we go in the homework tonight, we're giving you full permission to, feel free to do Taylor expansion by hand, but if you can ever kind of hack the system and use a known power series to get your result, we're giving you full permission to do that tonight, right? Maybe you can even think about how you might have done that with the square root of 1 plus x squared, problem 1 on the homework last night. Now, that might have been a little easier to do if we had thought about it in these terms. Yeah. Which one? Just the previous slide? Oh yeah, I will. I'm trying to think if there's one more slide. No, that was it. Okay. I'm going back to the homework slide because Laura's asking. If anyone needs